resistance in series, this is the meaning of resistance in series. That means they have only one terminal common. In that case, the effective resistance is sum of the resistance. And when there are two resistors which have both terminals common, there is nothing in between, then they are said to be parallel. And then the effective resistance is 1 upon R1 plus R2. You can take the LCM. So R can be written as product upon sum. Okay, so what is more important is obviously to identify whether two resistors or more are in series or in parallel. So that is a very crucial thing for you to understand. What is important over here is, in this particular case, the current flowing through them is same. Okay, so this is the same current. And in this particular case, obviously, you can see that the current get divided. Okay, divided means it will get bifurcated. It's not equal. It depends upon the value of resistance, but the same current is not flowing. Okay, so here it is I1, here it is I2. But what is important is there is the same potential difference. So I can say same potential difference. So when the resistors are in series, they have the same current flowing through them. And when the resistors are in parallel, they have the same potential difference applied across them. So let me take 3 resistors in series. And I have a battery attached and a key over here. So this is R1, R2, R3. And we will have current over here measured by ammeter. And there will be voltmeters applied to measure the voltage. And let us say there is another voltmeter that will measure the whole thing across. Okay, we'll call this as P and Q. So the potential difference across point P and Q is V, which will nothing but the sum of the potential drop in between. So from here to here and this point to this point. So V is equal to V1 plus V2 plus V3. That's important to understand. And as per here, current I is flowing. Okay, so the same current will flow through all of them. So I will write, since R1, R2, and R3 are in series, the same current flows through them. Okay, so therefore, according to Ohm's law, V is equal to IR. So I'm going to write this as I times R1 and I times R2 and so on. Okay. Also, if we replace this whole resistor, the 3 resistors, by a single resistor, such that if you allow the same amount of current, that is I. So I repeat, this I and this I is same. If the current is same, if the EMF is same, then the value of R is such that the voltage will also be same over here, this voltage we are talking about. So then the potential difference can be written as I into R. Okay, this is I into R. And here I is taken out. So this is R1 plus R2 plus R3. And this will be cancelled. And here you have R as R1 plus R2 plus R3. So the effective resistance, where R is effective resistance of R1, R2, and R3 in series. Okay. And also, before we conclude, we can say that if there are n number of resistors in series, okay, there are n resistors in series, then the resultant resistance will be R1 plus R2 plus R3 all the way up to Rn. N of them will be in series. So there are 3 resistors which is R1, R2, and R3, and they have current, the ampere A1, A2, A3, and they are connected to another ammeter and the battery, of course. And this current I is divided into I1, I2, and I3. And of course, the potential across each one of them is same, as we have discussed earlier. So when this current I enters this junction, that current gets divided. So here I'm writing I is I1 plus I2 plus I3. According to Ohm's law, what we have over here is V is equal to IR. So I is equal to V by R. So V upon R1, V upon R2, and V upon R3. So V is this potential difference. And again, if you replace this by a single resistor, okay, so you're replacing this by a single resistor such that it will give you the same current at the same voltage. So you are going to write V as I as V by R. And here this is R1, R2, R3. Remember, the statements which I'm orally saying need to be written down so that in your answer as a proof, if you just write these mathematical steps, you will not get marks. So this is the resultant of resistors in parallel. And if there are n number of resistors in parallel, then the resultant is 1 upon R1 plus 1 upon R2 and 1 upon R3 and so on. Okay, so this is the proof of resistors in parallel. Energy is neither created nor destroyed. It converts from one form to another form. So when you have electrical energy, it gets converted to various forms like heat. It's in a toaster or an oven. It converts to mechanical energy, okay, that is a fan or a washing machine. It gets converted to light in a light bulb. It does convert to sound, okay, in a speaker. So light does get converted into various forms. It can get converted to a magnetic energy also, electromagnet. So light, electrical energy does get converted to various forms, and we are going to measure that. So to begin with, we have the definition which we studied in this chapter. So potential difference is work upon charge. So we can say that work done is equal to potential times the charge. So I'm going to begin with this, okay, potential or the work done is potential times the charge. Okay, then what we have is electric current is rate of flow of charge. So charge is equal to electric current into time. So we have V IT as another form. So if I call this as number one, this is number two. So the third thing that you have studied is Ohm's law. So V is equal to IR. So if I replace V by IR, I will have W is equal to I square RT. So this is my number three. Or I can say that I is V by R. So I will get in this, okay, this is V by R. So I will have W as V square upon RT. So this is number four, okay. So these four formulas, we can say that these are of electrical energy. Electrical energy. Now moving ahead, we have power as work done upon time. So therefore, what we have is work is equal to, or we can say that power is equal to energy upon time. So when power is equal to energy upon time, if you divide all this by T, this T will go away. Okay. And what do you have? You have power equal to VI, power is equal to I square R, and power is equal to V squared by R. So this is a formula for electrical energy. And down you have the formula for electrical power. Okay. So in this, you have already learned the definition of SI unit of power as watt, but that was mechanical. And here, when you're talking about electrical power, So there is a new definition. So power is equal to VI. So 1 watt is 1 volt and 1 ampere. So that means there is a 2 points A and B, and they have a potential difference of 1 volt. And if 1 ampere of current is flowing, then the power consumed is said to be 1 watt. Okay, so that's another way of defining it. You have already studied 1 kilowatt hour in work energy power, but over here again we are studying that as electrical unit or commercial unit of electricity. So in our houses, when electrical bills are calculated, the power consumption of your house, they are calculated in units. So 1 unit of electricity is 1 kilowatt hour. So that means that is 3.6 into 10 to the power 6 joules. Okay, and to make our calculation easier, we are going to multiply uh, electrical energy, or we are going to find electrical energy in terms of kilowatt hour. So therefore, power has to be written in kilowatt and time has to be written in hours. So that's important. Okay. What else you have to know in this? Let's talk as an example. So let us say that there is a room heater, and a room heater is rated 1500 watt at 220 volt. Okay. So this is called as a power rating. So the meaning of power rating is that when the room heater is attached to 220 volt, it will consume 1500 watt of power. And let us say that it is used 2 hours every day. Then you have to find out that how much time it takes to consume 1 kilowatt hour of power. And second thing is in 1 week, how much will be the consumption? Okay. So number 1 kilowatt of power, how much time will it take? So therefore, what we have over here is power into time has to be 1 kilowatt hour. So power is 1500. I divide by 1000. So I get kilowatt. So therefore I get 1.5 into T as 1. So T will be 1 divided by 1.5. So that means it is going to take 1 divided by 1.5. That is equal to 0.67 hours. Okay, to consume 1 kilowatt hour. So that's one way of finding it. If you want to find in terms of minutes, you multiply this by 60. So you will get 60 divided by 1.5. That will be 40 minutes. So 40 minutes to consume 1 kilowatt hour. Second part is easy. One day, you consume 1.5 kilowatt into 2 hours because it is used 2 hours daily. That means 3 kilowatt hour in one day. Therefore, in 1 week, 3 into 7, 21 kilowatt hour is consumed. Okay. So this is a very simple type of question to expect in this. And then moving ahead to the last part is Joule's heating effect. So you have H is equal to I square RT. That means the heat energy is proportional to square of the current. Heat energy is proportional to resistance, and heat energy is proportional to time. So this means that if the current is doubled, so for example, from 2 ampere, you allow 4 amperes to flow, then the heat will become 4 times. If you allow current to flow through a higher value of resistance, the heat produced will be more. And if you allow current to flow through longer time, the heat produced will be more. So this brings us to the end of this current electricity chapter.